So let's talk about serverless compute. How many people use serverless compute in some form or another today? Wow, about half the room. So if you don't use serverless compute today, we're talking about sort of pure serverless offerings that you write some code, you upload it to a sandbox of some kind, you don't get a lot of visibility into how that code is executed, and you get the return of that code. There's other things that people label as serverless, like SQS or S3. We're not talking about those. So these are what people refer to as ephemeral runtimes, which means that they sort of come into being, your code executes, and then that environment, sometimes it's a container, is gone shortly thereafter. So why use a serverless thing at all? The primary reason that most people go to serverless compute is actually parallelism, because in an environment like AWS Lambda, more or less you have nearly infinite scale. Fan-out pattern style programming is very easy, and most programming models for it are event-driven, and you can hook automatic events up to other things in your cloud environment. In theory, this has more security features than your standard thick server. High availability is really simple, largely because you as a consumer don't have to manage it. It has enforced architecture patterns and little to no management for your ops team. So another way I like to put that, though, is that serverless is really hope by you, right? You're putting a lot of trust in the vendor to sort of do all the right things. And I don't always necessarily like to trust vendors. But we hope some set of things about these serverless environments. These are kind of the rules of serverless that we believe should always be true. We hope that our code executes securely. We hope that people can't tamper with the execution of that code. We hope that the vendor is patching the underlying operating system. We hope that our code hasn't been modified in transit to the sandbox. And we hope that this is somehow actually more secure than running our own servers, because maybe we're actually pretty good at that sometimes. So the things I hope you'll take away from this talk is how different vendors implement their sandbox. So this is isolation technology, really. Attack patterns and techniques for persisting in various environments, and how to build your own test tools to sort of hack around in the sandbox. This is the hacking part of the talk. Most importantly, I hope that you'll walk away sort of answering the question, should you use this at all, or should you avoid it entirely? So things you won't learn in this talk, because I didn't do them, is kernel-level exploits. I don't have any. You also won't see a container escape to the AWS hypervisor, because if I had done that, I would be selling it somewhere and not talking here. So we'll look at some Python in this, because Python is the primary language I write in. We'll look at a little bit of Node.js, which makes me sad. And we'll also look at some IAM policy docs. Quick favor, though. You need to remember that when we talk about the initial attack vector for the environments, it's that it's bad code. So we assume some sort of contrived vulnerability initially to get into the environment, because we assume that at some point you will make a mistake and some bad code will get introduced into your environment, and you'll have SQLI or an RCE, because this happens despite your best efforts, all your static analysis, all your quality controls. Someday this will happen to you. The question is, how bad does it get? Like, how dangerous is serverless compute when one of those RCEs is actually introduced? So before we get into that, let's look at who sells the serverless thing. Everybody, like pretty much every vendor that has an interest in cloud has an interest in serverless, because all these vendors get together, they compete with each other, and they seem to think that this is the future of the way that we will interact with compute resources. So Google Compute Engine has Google Compute Functions. Azure has Azure Functions. AWS had the first to market offering, which is AWS Lambda. IBM vends this project called Apache OpenWhisk, which is actually pretty neat. And then there's a couple small vendors in the space, the most notable of which is Offzero, who has an engine called WebTask. So what do people use serverless for? Probably nothing critical, right? It's brand new, hasn't been around a long time. The answer is they pretty much use it for everything. So kind of on the low-risk side, a lot of Slack bots are written in serverless frameworks. And on the high-risk side, you have things like Offzero, who is using the web task engine to provide OpenID Connect and SAML authentication for consumers in their public and private cloud environments. So while I was working on this talk, my boss tweeted at me that somebody had actually figured out how to run Docker containers in userland inside of Lambda as well. So this is kind of the moral of the story here, is that if you can figure out a way to sort of misappropriate a technology to do a thing, you can do it. And this was kind of my response to that, which is, why would you even want to do that? Because I think we already, frankly, have enough abstraction in these environments from an auditing and DFIR perspective, because we have containers now running in serverless sandboxes, running in sandbox containers, running in virtual machines, on compute hosts, all in the cloud. And as somebody who started their career in DFIR, this makes me nervous for some reason. I can't imagine why. So when I started working in IT, this is what a server looked like. You know, it kind of look like C3PO, and sometimes they restart. When they misbehave, you turn it off and on again. This is loads more complex. And so I wanted to know, what is the attack surface really of these things, and when they're breached, what are the potential pivots and persistence methods? So the attack surface is primarily in two places, right? It's at code execution time and in code pipeline. So this is like a code corruption style attack. So the first way we aren't going to talk about much, the code pipeline attacks, because if you can own the code where it lives in GitHub or something, you pretty much own the environment anyway. That's not very interesting, but I do want to mention it because there's kind of a hot topic in InfoSec right now, which is this concept of subdomain takeovers. And this is largely because of the way that technologies like Amazon S3 work, where you might go in S3 and allocate an S3 bucket to do a thing, and the name might be abc.xyz.com, and if you delete that bucket, somebody can immediately reallocate it with the same name. And then if they were storing source code in there and there's some other set of things chained to it, they can potentially pollute your deployment pipeline inside of the confines of their own account. So this is a problem when you publish all your code totally in the open, and these kind of attacks really do happen in the wild. So the other way that you can attack this is actually at runtime, which is far more interesting, right? So this is the concept. In this diagram, I have a web app represented. You're actually attacking through Amazon API gateway into the Lambda sandbox, and then depending on how lax the IAM policies are, and we know that people are bad at AWS IAM, they're getting better, but it's still really hard, you can pivot to other things in the environment from that sandbox. So maybe that's not very interesting. It's kind of all the usual attack techniques, but it's kind of interesting because people are forklifting existing application workflows, sort of similar to when we made the transition from data center to EC2 initially. Now we're making a transition from EC2, and we're taking those apps, just like the Docker container idea, and we're shoving them into serverless. So maybe there's some unique considerations here that we need to know about. So there's two things we're primarily concerned with when we talk about attacks on serverless environments. And they're persistence and data exfiltration. And this goes back to all the things that we hope are true about serverless compute. The most notable of which is that we believe as consumers that these sandboxes get thrown away at the end of their life. We have to be able to take it to the bank that this happens in order to trust the environment. We also believe, because these are serverless, that they have maximum execution runtimes. And that should always be true too. So in AWS Lambda, the limit for code execution is 5 minutes. It's supposed to go 5 minutes. If your code goes 5.01 minutes, it should die, whether it's done or not, and then it should go away. So 5 minutes is a lot of time if you have the right type of attack, right? You can do a lot of things in the environment programmatically in 5 minutes. That's an issue. And before we dive into what those things are, let's talk about a couple other terms. So term number one is cold start. So this is what happens when you first execute some code inside of a serverless environment. The provider, Amazon, Azure, GCP, has to allocate some compute resources to you. They have to stream the code down to that container and load it. So this takes a little bit of time. It's about a half a second penalty each time that you have a cold start. And so providers introduced this feature called warmness in the name of performance, which is that if you invoke a function multiple times, that code will actually stay on the compute host that was executing it, and you may or may not be returned the same container on subsequent executions if they happen in a certain time window. So you can kind of see where I'm going with this maybe. So the first person to talk about this warmness versus cold start concept was Rich Jones, and he actually writes a serverless framework called the Zappa framework. And this framework pretty much allows you to take a Flask app or a Django app and more or less forklift it into AWS Lambda without having to modify the underlying application. So he was doing a lot of work in Lambda, and he gives a great talk called Gone in 60 Milliseconds about data exfiltration. You should check it out. I linked it in the slides. So these environments have two attack surfaces. They have the outer attack surface and inner attack surface. On the outer attack surface side, we have AWS API Gateway. This is kind of a black box reverse proxy. You don't really get a lot of visibility into how it does what it does. It costs $4 a month to have it in your environment, and it hooks up all of the routes to the underlying application. On the inside, you have the actual AWS Lambda functions, and then under that, you have some set of other services, which are kind of the chocolatey center that as an attacker, you want to be able to go and take over those other services for your exfiltration or persistence. So when you're scanning for these things in the cloud, the way that you identify that it's a serverless app might be based on things like HTTP headers. There are some dead giveaways that something is running inside of AWS Lambda. This isn't like a smoking gun necessarily, but you can look for the header XAMZ CFID, which just pretty much indicates that something is coming from CloudFront, but API Gateway also discloses that information. So you can say, maybe this is Lambda. On the Offzero side of things in the web task engine, it actually identifies itself in a header as web task. And on the Azure side, it's just IIS. So we don't actually get any disclosure. Maybe this is intentional, maybe it's not. But no smoking gun there on the Azure side. You can also do some recon on GitHub to see what apps are being deployed in serverless. There's a popular framework called the Serverless Framework. Surprise. It has a config file, serverless.yaml. You can see there's quite a lot of results here. You can sort of dig in and see how people are constructing their apps and where they're deploying them. So when you find the serverless apps, what do you do with them? I didn't know the answer to that. So I wanted to kind of dig around and see what was possible inside of each execution environment. And so I went out and I actually looked at the vendor docs to see if any vendor was super transparent about the way they allocated resources and put together their sandbox environments. And I didn't really find anything. So most vendors consider their serverless technology to be super secret proprietary sauce, right? They won't even say it's a Docker container. But we can know that it's a Docker container by sort of poking at it a bit and seeing if it behaves like a Docker container. Because if it looks like a duck and it quacks like a duck, it's probably a duck. So I personally have a problem with using things that I can't understand, which is why I love open source software, right? I can always rip open the code and know how it works. So I started writing some code in Python that I would deploy into these environments that would literally run OS shellout commands and learn things about the environment. And this was based on another project by a guy by the name of Eric Hammond, who wrote a web shell wrapper in Node.js to just execute bash commands. So I started kind of evolving this until I had a bunch of checks that would more or less try to know all the things about the environment. Was it Linux? What was the kernel version? What kind of processors did it have? How much memory? If it was Python, what were the Python packages? What were the versions? Are they up to date? How long was the host alive? How long was the container alive? What's the networking like? Can I exfiltrate data through a NAT gateway? And so I built all these checks up. Here's kind of like the list of things I primarily wanted to know, though, based on an analysis of that data. I wanted to know, is this a regular operating system like RHEL or CentOS or Windows? If so, are the general things about that OS true, or has it been modified by the vendor in a way that's proprietary to make it more secure? Which sort of led me to ask, can I read and write everywhere in the operating system? If I can I poison my code via an RCE? Can I modify the actual code that's loaded into the runtime? Can I get and set environment variables? And are the permissions in the cloud too permissive or just right? And what about internet egress? Because if I just get any internet access I want, that makes it really easy for me to just do one data burst of any set of data that I got and make that kind of hard to detect and, slip away with lots of great data. So this is a little bit in the cloud like playing operation, right? So I totally don't advise that you do this until you have a frank conversation with your vendor that you're going to audit their environment, because depending on what you're doing and what vendor it is, you will trigger their actual automated user protection, and you'll get kind of a cease and desist notice. And so I work with Azure and AWS and Offzero pretty tightly during this project. So if you're interested in doing this, I can connect you with the right people. So I looked at Lambda, Azure, and Auth0 Webtask. I'm actually in the process right now of also doing this for Google Compute Engine, but that data will not be publicly available until January. So if you follow me on my website, you can get that data at the end of the year. Let's talk about Lambda first, because Lambda is kind of the easiest. It's the longest-lived serverless runtime. We know a few things from the research of other people, not necessarily from public vendor docs. We know it's some kind of container-based system. We know it runs on Amazon Linux. Big surprise there. Amazon Linux is just a RHEL derivative. It has a read-only file system. Code is injected into var run task. Code executes as a non-root user. There's a single AWS IAM role accessible to the sandbox. Reverse shells are not possible because of AWS NAT gateway magic. Somebody tweeted at me to correct me on this point. There is a way to get reverse shells in Lambda, but it assumes a lot of custom configuration. It's really hard, so I'm going to stand by that statement that under normal circumstances, you can't get reverse shells in Lambda. And you can get internet egress, and in some cases. By default, your functions do have internet egress. So I wanted to know if I could steal the credentials. Were the credentials inside of these functions special in any way? And if I can, how bad does it get? Where can I persist code? When I do attack it, how long can I persist code? And then can I get Lambda to do things other than execute code in the language I prefer to use? So this is kind of like a two-stage attack. I get an RCE, I stream down an arbitrary binary that maybe does some nastier things. Should Lambda prevent the execution of that? And how frequently, lastly, does the OS get patched? Because we know patch management is kind of a hot topic because Equifax. So I won't dive into the sample output here because the internet access in this room is really terrible, and frankly, I'm terrified to leave my slides. But this is a blob of descriptive JSON. Just picture the most descriptive JSON about the sandbox that you can think of in your mind. So this is what the container structure looks like from my analysis of that JSON, right? It's just a regular Linux file system connected to AWS API gateway. The code streams down. There's a magic file that nobody talks about in here called bootstrap.py, which has tons of juicy stuff that I could have spent a long time analyzing, but this is how Amazon does X-ray. This is how they talk to other proprietary things in Amazon to instrument the container, and lastly, it's also how they hook up, whether it's Python or Node.js. So that file's kind of interesting. You can dig into that. There's also /AWS Lambda directory, and then down at the bottom there, there's only one writable directory in the whole thing, which is /temp, which is actually a RAM disk. So if you slide little slider in Lambda and you allocate 512 megs of RAM, it'll actually make a /temp partition that's 512 megs. And that's the only place in the container that you can persist. And then on the side there are how the credentials are delivered. Some things in AWS use the metadata proxy service, if you're familiar with that. It spins up a web server on 169.254, 169.254. These don't have that. You can't access the metadata service. All the creds are delivered as environment variables, which are just temporary session tokens that are valid for an hour. So that's how the creds live in the container. So given these limits, because the attack surface is really, really small, the container is really, really limited, as an attacker, you can kind of laser focus on how you're going to design a piece of serverless malware. right? Your initial payload needs to be as small as possible because maybe you can only get it into the sandbox via API gateway. There's maximum sizes for get, put, post requests potentially. You need to persist it in temp. Temp's really small, maybe 512 megs in a lot of cases, maybe 128 in others. You need to be able from inside of your malware to assess lateral movement in the environment as fast as you can. And if you can't pivot, you need to just die because maybe you're going to be detected and you need to exfiltrate your results to somewhere else as quickly as you can before the container exits and dies. So, in other words, your attack needs to be bigger on the inside. So there's some great ways to do this in Python. So Python minification is a thing. So you can write Python, you can run it through Python minifier that basically takes all of your Python and it kind of cross-compiles it to totally like non-human understandable Python Lambda statements and smashes all the white space out of it. So that's one way you can get your Python really small. It even supports inline compression. And then when you're building your Python to do reconnaissance, you probably want to know what you can do. So inside AWS Lambda, you get the Boto 3 library for free, which is AWS's interface to all of its APIs. And so this is kind of an example of how you might write some Python that would brood out the permission as to whether that function can create CloudWatch Log groups, which is probably a great way to exfiltrate data. If you can do that, just to create a CloudWatch Log group, put your stolen data to CloudWatch logs, and then pick it up later from some other service or a subsequent execution of the function. And so I wrote a bunch of samples of this, and there's a GitHub gist in here with kind of a reconnaissance script that I used. There's also a Python module called Oneliner Iser that will take any Python script and turn it into one totally unintelligible line. This works great if you want to make serverless malware. I didn't make serverless malware that I have to share with you, but boy, that sure would have been cool. Maybe next year. So in summary, you have two techniques with lots of payload packing. And if I was writing serverless malware, that's probably how I do it. Instead, I decided to build an app that was vulnerable and just sort of attack it by hand. So I wrote a Slack bot because people use Slack for a lot of things. And that Slack bot's primary job was to take a webhook from GitHub, send a notification to a channel, and then allow a user to ask a question of that Slack bot about commit messages. But I put a vulnerability into that Slack bot that allows you to get a string escape and execute arbitrary code. And so I have a little demo of that. This is what the normal behavior will look like. This is what the bad behavior will look like. You can see I have the Slack bot sort of vomiting creds back into the channel from some code injection. And you can escalate the behavior of that. But the video sort of tells the story a little bit better. Hopefully that's big enough. So let's fast forward to the juicy stuff. This is me making fun of my co-presenter at Black Hat in the Slack channel while I'm performing the attack. So there's the commit message that says, hey, somebody committed some stuff to GitHub. This is normal behavior, and you can ask it to go get the changelog for you. And you can inline a file name between some sort of templating style language. And so this is me asking it to do the regular thing, go get the changelog, and copy that into the channel. Look, there's the changelog. That was ASCII Star Wars, but Slack does not honor ASCII. And so this is just me validating that it actually did go out and get the changelog. So again, me making fun of my co-presenter. And so there's the vulnerability. It calls os.popen, and it does a shell out instead of using native Python read facilities. So kind of unsafe. So this is me inlining just a list command in there to validate that it actually works. And boom, yay, I know we can do stuff. So now what else can I get? Lots of juicy stuff is maybe if I'm root. Definitely not root. I'm SBX user, which is the regular user for AWS Lambda, dead giveaway. I know from other stuff and things that environment variables are where the creds live, and so I get the creds. Yay. And so then I want to know stuff. and things about those creds. So I just copy them into my regular Boto profile. And once they're in my regular Boto profile, I try to call S3 with them, and I can't because this is a hardened IAM policy, but this validates that the creds do work outside the sandbox. I can know who I am, and then I can run Daniel Grzelak's AWS pwn to see all the other stuff that I can do. So this is a script that you can run locally that just goes through and it will brood out all the permissions more or less by just trying every permission in every service one at a time and recording whether it was authorized or unauthorized. Now that's a really noisy, very stupid attack if you actually care about somebody not noticing you, but you can do that. So you can also get artifacts out. This is me basically proving that you can post to other places on the internet. So I wrote that test to see if I could create log streams and then report the status back to yet another serverless function, so using serverless to collect data about hacking serverless. So it's serverless inception. The attack surface of these kind of attacks becomes larger with bad IAM. And the issue here is really frameworks. So this is new technology, right? We're still making a lot of custom tooling around making it easy for developers to interact with. And a lot of the frameworks like SAPA and Apex framework do not make good IAM policies. So this is the default policy of a Zappa deployment. And if you know much about AWS policies, maybe you don't know much about AWS policies, all you really need to know is the more stars there are, the worse it is. And this has a lot of stars. So the IAM struggle is really, really real. My boss likes to say that IAM in AWS is the killer feature and the killer feature. So detection is also kind of difficult here. On-premise, we have a lot of mature facilities for seeing if our environment has been breached. We have network taps, we have audit D, we have syslog shipping, other SIM functions. In the cloud, we basically have CloudWatch logs in AWS. And anything else that we do to instrument our own applications. And so if I have one piece of advice about this, it's that if you're designing an application for serverless, don't leave your time machine in the garage. Like, make really heavy use of CloudWatch logs and actually have developers write sane logging into the app that proves that it's behaving normally. Because you don't really have a ton of native instrumentation in the environment. So, I did my demo early for the bad Slackbot app, so just pretend that it happened here and everything went really smooth. So when I did that demo of the Slackbot app, I had CloudWatch logs turned on, and you can see that there's some abnormal things that end up in CloudWatch logs if I'm using them. There are definitely lots of great indicators of compromise for the environment here. So besides just the fact that I had shell commands in my CloudWatch log, I had anomalous execution times for those functions. So one of the things that AWS CloudWatch gets natively is it gets the execution time that it took for a function. So you can definitely, in some cases, average that, and you can know if it's within standard deviation of the mean, right? And anything that's outside of, maybe like 1.25, you should trigger an alert on. High error rates are a dead giveaway that something's gone wrong. And CloudTrail high denials for the role in Lambda is another sort of smell test that somebody might have exfiltrated some credentials and is doing bad things. This is what the CloudTrail event looks like for a deny. CloudTrail deny events do not surface in the regular AWS CloudTrail interface. You don't see them unless you look at CloudTrail in CloudWatch or you look at the raw data. So a lot of people that I talk to don't even know that CloudTrail logs denials, but it totally does, and you can use this. So bottom line about Lambda is that it's only as bad as your IAM and AWS cases, and you can detect it through CloudWatch Log delivery, but your mean time to respond is about 7 to 10 minutes in a best case because of the way that CloudWatch logs bubble up in the environment. So now let's talk about Azure Functions. Azure, unsurprisingly, runs on Windows. It has a set of functions grouped within what they refer to as apps. Because it is Windows, and Windows is built in a very specific way, the file system in these is largely writable. It does not have internet egress. Everything runs as non-root. All functions in the same app share a system or tenant. All functions in the same app execute as the same user, app code is loaded into a root in a drive that's called D that's attached. Code gets injected into an IIS root, unsurprisingly. Some secrets are stored in data functions secrets, and that's going to come into play later, how Azure sort of mismanages those secrets. So I wanted to know the same questions I asked about Lambda, and since all these things, unlike Lambda, get deployed onto the same tenant, how could I use that functionality to maybe do bad things to a single app? So a couple other tidbits about Azure that they do publicly disclose is that you don't get WMI access, and get event log list does return objects, but not in the way that you think. They actually send all the Windows event logs to dev null for some reason. So in digging around, I use the same programmatic shell wrapper as before. It's a less ephemeral system, so it means I have more tools at my disposal potentially. Azure does open source this sandbox to its credit. It's available, but in the Microsoft Developer Network documentation, they don't actually say that they open source it. They actually open source it under a code name called Product Kudu, and they don't really marry those docs together to make it easy for you to know. You can run PowerShell in the environment. We all know that InfoSec people love PowerShell. And that greatly reduces the pain of understanding how the environment is put together. So in order to demonstrate this, my colleague, who is not here co-presenting with me, created a vulnerable app concept that was supposed to be a credit card batching API. And it does very much work like a credit card batching API, and it's composed of a few different functions that are single responsibility that are designed to do things like accept credit card numbers, charge someone, and then bill them at the end of the month. So it's written in Node.js, and so we introduced a little vulnerability here that allows you to execute some arbitrary code and get a function to return before it's intended. To Azure's credit, this when a function does return early, it raises a red flag in the log, but it still does execute all the way to completion. Here's the indicator that a function has returned early. It'll say error done has already been called. Please check your script for extraneous calls to done. That is a smoking gun. That means somebody got RCE in your function. So if you're a visual learner, all the functions live on the same tenant, and any function inside of that tenant can, by default, list all functions that run on the tenant. So immediately you have API access if you gain a foothold in a low privilege function to know what the other functions are. You can change API keys from inside one function for any function on the same tenant. So this is bad. You can change the triggering methods of other functions. So let's say that you have a credit card batcher app, and some of the things are event-based from a REST API, and you have a billing function that's supposed to send bills out every month. You can change that billing function to run on an event trigger instead, or run every minute. And lastly, which I will show you in an Askinema demo, you can actually, from a low privilege function, poison the code of a higher privilege function. So I think I'm running a little bit behind here, so I'm just going to skip to the juicy stuff, which is changing the source code of the function. Here we go. Internet access is hard. Oh, yay. There we go. So what you're going to see on screen before I actually click the play button on this is a post with curl that will cause the billing function to say that my credit card bill, instead of being what the normal charge is $1. And the way that it will do that is by hitting a low privilege function with an RCE. It will list all the functions. It will ask for the API key for the high privilege billing function, and then that API key will be encrypted. But since all the functions run on the same tenant, and Azure is perhaps not as mature in their IAM model, I can actually just very nicely ask Azure KMS to decrypt that API key for me, and it will return me the key. And then I can use that to access the high privilege function. So when this happens, even though it will be unsensational, you need to clap. For my co-presenter who is not here. There it goes. Got the bill back. Now I'm going to patch the billing code to always return $1. And then I'm going to ask it what the charge is at the very end, and it should say $1. So, yes. The bill on the left there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, is now $1. And the other charge has been moved to another credit card number. All of the code for this is totally public, by the way, so you can deploy this in Azure and you can play around with it yourself if you want to test the IOCs out or you want to test the API key thing. All right, moving right along. So takeaways from that. Having separate API keys is great, but once you're in one function, you have access to all the other API keys, so you might as well not have many. It's only inconvenient for you. Be aware of the choices that you're making by putting functions in the same app. I actually think this is a bad piece of advice that's given for a feature that was intended to work this way. So the default blueprint is for all your functions to deploy in one tenant. If you want to work around this, don't deploy all your functions in one tenant if they have separate security boundaries. You can make this secure. It's not that hard. It'll cost you more money. But when you're talking about running functions for a fraction of a cent, if it costs you 0.002 cents instead of 0.001, who really cares? So the last vendor I'm going to talk about is Offzero. Offzero Webtask is probably the smallest runtime I looked at. Webtask is, to Offzero's credit, totally open source. It runs in Docker containers on CoreOS. They are very transparent about that. It allegedly runs Node.js only. There's no restriction on internet egress. This is because of the nature of how Offzero works. They are an identity provider. And it would be very hard for an identity provider to have compute environments that could not talk to other things on the internet. It's used inside of the Offzero rule engine and lots of other stuff like GitHub webhook-based applications. It has public and private tenants. You can give them lots of extra money to run your own instance of it. So at first I thought, oh man, it runs Node.js. I have to re-implement all my code that mines the sandbox in Node, and that sucks. But then my coworker actually figured out that you could just circumvent the actual native sandbox protection that prevented you from calling other things by just launching sub-processes. And so, yay. He wrote a web shell for me to use. His Twitter handle is Kingster Iser, and if you think this is cool, you should go follow him on Twitter because he tweets about lots of other neat things. He's French. That's a French name, by the way. I won't even try to say his actual name. It's Guillaume. And so that's the output of the web shell running inside the sandbox. And so now I didn't have to do much, right? Because I could get the sandbox to do whatever I want. I could also run Python in the sandbox. So once I can exec child processes, I pretty much found out I can do all the things. And so we found a couple other things while we are digging around in here, one of which is a raw socket that's mounted inside the container as a shared Docker volume, and that was interesting. So I'm going to show you a quick process demo. And so this demonstrates that Offzero does not follow one of the rules of sandboxes, which is that we believe that sandboxes die at the end of their maximum execution time. I lost my web task session. Oh, it is definitely not webtask.com. We are so lucky that that was a benign site. The tubes are slow today. So it has a nice IDE, while I'm sort of dancing up here waiting for this to load, where you can just write the Node.js like right in the browser. All right. So now we can pass arbitrary arguments. And so if I type something that actually like forks a process to the background and sticks, like Python, that would pop the Python interpreter, this sandbox will just stick on the tenant until another process comes and sweeps it away. So just by forking a process, I can keep this container alive longer than the intended execution period, which is lame. Sometimes this works, and sometimes it doesn't to run PS because it associates something with my IP. There. So that's proof. 2 tabs, Python still running in this. If I just sit here and refresh, oh, that one died. So maybe they've improved this. But if you watch the Black Hat demo, this totally works, I swear. All right, Offzero learnings. I left my slide deck, came back, and it still worked. Forked processes hang the container. Maybe they don't anymore. Backchannel.sock is a socket that is a REST endpoint, likely for credential exchanges during auth. I didn't poke at that too much. Sandbox is escapable to the container. Sandbox system is Debian with little anomaly detection or monitoring during the entire time that I did super noisy things in here, including running several Docker exploits. I didn't trigger their automated protection, which is a little unsettling. And so I decided to kind of start a project to put this all together, all this data, all this profiling. And so I had the Serverless Showdown project, which is all those things I gather from Python, lots of tests. It matters because as consumers, we need to know when the environment changes. We need to know how often the vendor patches because there's no such thing as a patch feed for serverless sandboxes. And it allows us to really keep the vendors honest with us as consumers. And sometimes it'll give us clues when new features are coming out because you'll see new environment variables for NDA services kind of popping into these containers before they're actually publicly released. I don't know how you could use that to financially profit. So I decided to make a project called the Serverless Observatory. At Mozilla, we love things that do observatory stuff and things, and this is not a Mozilla project, but we have the Web Observatory, and it inspired me to make the Serverless Observatory, which is still not done, by the way, because I am a busy guy, but if this is something that you're interested in being a first-time or many-time open source contributor to, I would love to collaborate with you. It is actually a project with an API, allows you to sign up and send profiles to this, and then it'll run a bunch of tests on the profile and score the serverless sandbox. And I made this in an abstract way so that it can run in any container environment. So you could really use this to test any serverless engine out there and get back an A through F grade based on some opinions that I have that are actually derived from the Docker CIS benchmark. So if you think this is cool, sign up for my mailing list on threatresponse.cloud. That's my website for the open source project that I presented here last year and the year before. Yeah. So how did the security features stack up across vendors? This is a cool slide to tweet. This is how all the vendors implement the controls I think are most important. So none of them restrict the language that's executing. This is bad. Only some of them have read-only file systems. All of them actually, to their credit, do patch very frequently. AWS has the most granular IAM. AWS is the only one that you can deploy functions that don't have internet egress. None of them have immutable environment variables, and that's not really the vendor's fault. That's just kind of the way their operating systems work. So if you want to give something back to the world, give a PR to the Linux kernel that makes environment variables no longer writable sometimes. I hear this is an impossible problem to solve because things. And almost all of them have some kind of warmness concept. So if I could ask the vendors to do things for me in this magical world where I can get all of Amazon to deliver me a feature, what would I ask for? I would ask for any control that requires out-of-sandbox levels of access to implement. So that would include things like native code signing protection. So if I use PKI to sign my code, I don't want it to execute if it's not mine. I'd like immutable environment variables. I know it's hard, but They have lots of employees. I'd like the ability to choose cold start in favor of security. So that warmness capability we talked about that's in favor of performance, if I don't need it, I'd like to be able to choose to turn it off. Maybe I'd even like to pay less for that. I'd like the ability to kill any process that's not executing in the language that the runtime has selected automatically. And I'd like more transparency in the patch cycle and trade secrets of the runtime, because the more things I know as a consumer, the better choices I can make about the risk of running things in that environment. So should you use this? Probably. It's probably still better than startup-sized OPSEC or something, and being able to lead on a vendor for this is still good in most cases. But you can limit the blast radius of these attacks. You can use event-driven security in Amazon, like CloudWatch events, CloudTrail, and automated response, like the project I make, Threat Response. Remember that name? Threat Response, Threat Response, Threat Response. I make an auto-IR pipeline for this stuff. So I'll leave you with this one last quote before I take a few questions, which is that modern security does not resemble high walls or strong doors, but rather bells on strings that ring each time an attacker moves forward. So all these people contributed to my project, and there's actually a couple people here today that contributed to my project. My boss, Jeff Briner, and Danny Hartnell from Mozilla. Both were contributors to this profiling project. I could never have done this alone. It was a ton of work. And also my co-presenter, Graham Jones, who works for a Portland-based company, LegitScript, was my co-presenter at Black Hat, and he did the lion's share of the Azure research. So I got to mention him. So vendors were really nice too. Thank you to them. And now I'll take questions. I'll be in the hall, and I'm also running the CTF. Come find me if you want to talk about general cloud stuff and things.